Hey, hello students. I really miss you guys. It's been a while since I saw all of you. Um, well, I made this video before while I was still with you, so I don't know, maybe I don't miss you. But anyhow, let's get this lesson rolling here. Chi-square tests. Pi, the mysterious number pi. Mathematicians have been analyzing this number for many, many, many years, and we have not found a pattern, have we yet? Well, maybe we should look at a different angle. Maybe there's no pattern in pi. We know it's an irrational number, but what if we examine the number of times each digit appears? Did you ever think of that? Maybe 5 appears more than any other digit, or 7 or 9, or, let's take a look at that. Well, somebody did that for us, and here's what they got. Now, they did the first 1 million digits in pi, so obviously, we can't do them all. We did the first 1 million, and there's the breakdown. So the question is that there are differences. They're not all equally distributed from 0 to 9, but are the differences significant? That is our question all the time here in this class, right? And for that, we're going to have to use probability. But this is unlike any other test we've done so far. We have a whole list of numbers, and we want to compare that list to another list of numbers, the expected. If, in fact, they were equally distributed, we assume that's true, right? We assume no difference. That's the null hypothesis. Then we would get that, right? We would have 100,000 of each digit adding up to 1 million. How far apart are these? So we have to check the entire list to the entire expected list. So here's how we do it. We're going to first just simply subtract observed minus expected. Boom, right there. Then we are going to square each one. Kind of like the standard deviation when we did that. We don't want negative numbers, so we square all of them. Then we are going to put them in perspective. In other words, these numbers are huge, right? These numbers are large. But when we're relating it to 100,000, are they really that large? And that's why we divide by the expected. For example, these differences would be considered very significant if your expected numbers were maybe 200. These numbers would be very significant. But because our expected is actually 100,000, are these significant? Well, maybe. Let's see. That's why we divide by the expected, to put it in relation to the expected. And there we have a bunch of numbers. Now, if you add up all of these numbers in this column, you get 5.51. That, guys, is the chi-square score. And there's our chi-square score. Now, what we just did was called a goodness of fit test. How well do the observed fit the expected, essentially? Conditions, conditions, conditions. Well, what are they for this test? All of our data must be in counts. So we're not dealing with percentages here. Every value is a count, which we had. We always have to have independence or randomization. Now with pi, that's not really the case here, but that's what we need to have in general. And all of the expected cells must be at least 5. Well, our expected were 100,000, so we have no problem with that condition. That just assures that you have a large enough sample size. Your HO and HA are not going to be in symbols or numbers. They're going to be just in words. Create a phrase or a sentence. Now, null is still always no difference, or in this case, the digits of pi are evenly distributed. Alternative, then, is that they're not evenly distributed. There was the chi-square score that we calculated. Chi is a Greek letter, and chi-square, because we did square them all, right? And it's the sum of what you see here, which we showed you in the table. You're going to do that for each goodness of fit test. Degrees of freedom, that's going to be your categories minus 1. K for categories, right? In this case, we had 10 categories, 10 different digits we were comparing. and the good old p-value, which helps us make our final decision, you can do on the calculator. Chi-square CDF. Same place you find normal CDF and TCDF. Now this requires the chi-square minimum, chi-square maximum, and the degrees of freedom. So then you can put in the chi-square score of 5.51 as your minimum. We're always going to be going to infinity to the right. All chi-square tests are right-tailed. And we're going to use 999 here, guys, because chi-square scores go a little higher than our t scores or normal scores. So we want to use 999 here, and of course our degrees of freedom. And you will find the answer. Go ahead and plug it in yourself and find out whether the digits of pi are evenly distributed or not using your p-value. All right, what about a table? We just did a list versus another list. What about a table? Here's a good example. Eating fish. Good for you, right? What about specifically for men and getting prostate cancer? There's been some anecdotal evidence of that. Well, here's some data for you. We have men who have told us how often they eat fish, 4 different categories. And we tracked these men for a long, long time, and we tracked how many got prostate cancer or not. So we can't really compare one list to the other because we have 2 different variables here. This is more of a table. We don't expect these 2 to be the same. So we're not comparing one list to the other. We're comparing whether one variable has an effect on another variable. Are these 2 variables dependent or independent? Well, a chi-square test fits in here very well too. Here's some of the mechanics involved there. HO and HA, words again. But here you're going to use independent for HO, meaning no effect, right? Independent means one does not affect the other. And HA is going to be that fish consumption and prostate cancer do depend on each other. Degrees of freedom is a little different. You take your rows minus 1 times your columns minus 1. This is just your data, not your label columns or rows. So we had 4 rows, so 4 minus 1 is 3. We had 2 columns, so that would be 2 minus 1. So we have 3 degrees of freedom. Now you need to create an expected table. This nifty little formula here actually assumes that there's no difference, that the variables are independent. So if you follow that, you will find the expected table, and I have that for you here. Well, we'll see that once we just show you this. The chi-square formula is the same, and conditions are the same as goodness of fit. Here's that table. Here's the original data table with totals, and here's the expected table down here. Now, just to show you, how did I get 9.21? Well, you follow this nifty little formula. This cell matches with this cell, the 14, right? So I would take the row total, which is 124, times the column total, which is 466, divide that by the table total, and you will get 9.21. Let's do one more. How about the 201 cell? This matches up with the 194. Now for this cell right here, you would take this row total, 2621, times this column total, 466, right, divided by the table total again, and you get 194. So the chi-square score, you have to do 8 times, kind of. You have to take 14 minus 9.21, square that, and divide by 9.21. Do it again. You take 201 minus 195, square that, divided by 195. So it's the observed minus expected squared divided by expected. If you do that for all 8, I have these in a little table itself. These are your 8 chi-square components. You add those 8 components up, one for each cell, using this formula. you will get the grand total chi-square score. In this case, 3.68, which gives us a p-value. So if we do chi-square CDF from 3.68 to infinity, 999, with 3 degrees of freedom, we get that p-value. Surprisingly, not significant. So apparently the fish didn't show a significant difference in preventing prostate cancer eating fish. Here's how we want to say that in a conclusion. Assuming getting prostate cancer is independent of whether men eat fish, there is a 30% chance, that's from here, of getting results more extreme than ours. This does not show evidence of a link between the two variables. Hey, I will see you guys very, very soon. Have a great one.